Enthalpy changes and equilibria. Matter contains energy as both kinetic and potential energy. The kinetic energy is the energy of motion at a molecular level, the vibration, rotation, and translation of atoms, ions, or molecules. The potential energy arises from the positions of atoms relative to each other, and both bond breaking and bond making involve changes in potential energy. We cannot measure the amount of energy a substance contains, but we can measure the energy change when a substance is converted into a new one. If the reaction is carried out into an open container, so that any gases produced can escape, and the pressure remains constant, then the energy change measured is called the enthalpy change. So the enthalpy change is the change in heat energy at constant pressure, and is given the term delta H. In an exothermic reaction, heat energy is given out, and the reaction gets hot. But where does this heat energy go? It goes into the surroundings. The change in enthalpy, delta H, is the total enthalpy of the products minus the total enthalpy of the reactants. The total enthalpy of the product is lower than that of the reactants, as energy has been given out as heat, so delta H is negative. To recap, exothermic reactions are accompanied by a rise in temperature, and delta H is negative. In an endothermic reaction, heat energy is absorbed from the surroundings, and the reaction mixture cools down. The total enthalpy content of the products is higher than that of the reactants, so the change in enthalpy, delta H, is positive. Okay, so endothermic reactions are accompanied by a drop in temperature, and delta H is positive. Enthalpy values are given under standard conditions, and a standard enthalpy change is denoted by delta H theta. What are the standard conditions? All gases should be at 100 kilopascals, or 1 atmosphere. All solutions should have a concentration of 1 mole per decimeter cubed, and be at a temperature of 298 Kelvin. The first law of thermodynamics states that energy can neither be created nor destroyed during a chemical change, and Hess's law is the first law applied to changes in heat energy. Hess's law states that the total enthalpy change that occurs when going from reactants to products is independent of the route taken. It allows us to determine those enthalpy changes that are difficult to obtain directly by experiment. You should be able to calculate enthalpy changes using standard enthalpies of formation, standard enthalpies of combustion, or mean bond enthalpies. But in order to do so, you need to know exactly what is meant by each term. So the definition of the standard enthalpy of formation of a compound is the enthalpy change when 1 mole of the compound is produced from its constituent elements in their standard states under standard conditions. The important parts of this definition are the formation of 1 mole of the compound, and that all the elements and the physical state in which they exist under standard conditions, 298 Kelvin, and a pressure of 100 kilopascals. Remember, in all chemical equations involving enthalpy changes, the physical states of all the chemicals are shown. Let's look at an application involving the calculation of an unknown enthalpy change using standard enthalpies of formation, we can now construct a Hess cycle. Remember that the total enthalpy change in both routes are equal. The standard of enthalpy of combustion of an element or compound, delta H theta C, is defined as the enthalpy change when 1 mole of the substance is completely burned in oxygen or air under standard conditions. The term completely burned means a complete combustion and not partial combustion takes place. In the case of ethane, C2H6, it is represented by this equation. Notice that water is in the liquid state, in its physical state at 298 K and 100 kPa. Let's look at a typical calculation. We can now construct a Hess's law cycle. Applying Hess's law, there are two routes that can be taken. The total enthalpy change in both routes are the same. This equation is the opposite way round compared with calculations involving enthalpy of formation, just like this. Calculations involving bond enthalpies only apply to compounds containing covalent bonds. The bond dissociation energy is the energy that must be absorbed to separate two atoms in a particular covalent bond. But even in a molecule like methane, which contains 4 carbon-hydrogen bonds, the energy required to break each bond individually is different. So, we must use the mean bond enthalpies in our calculations. However, for diatomic molecules such as chlorine, we can use the bond dissociation enthalpy. The energy required to break all 4 bonds in methane is 1,664 kilojoules per mole. The mean bond enthalpy of the carbon-hydrogen bond in methane is 1/4 of this. The value of the mean bond enthalpy of the carbon-hydrogen bond given in the data book is 413 kilojoule per mole, slightly lower than our value. This is because it is an average taken from many compounds containing the carbon-hydrogen bond. So, because mean bond enthalpies are average values and not actual bond enthalpies, the enthalpy of reaction calculated will be an approximate value only. There are lots of reactions for which the enthalpy change can be measured by experiment. In order to determine an enthalpy change directly, you need to measure the amount of heat energy taken in or given out, and know the number of moles of reactant used up. For reactions that occur in solution, the heat is given out to or taken in by the solution itself. The experiment can be carried out in a polystyrene beaker so that no energy escapes from the system to the surroundings. Typical reactions that are carried out in this way are neutralization and displacement reactions. Let's have a look at a calculation. The enthalpy change is a negative value because the temperature rises. Heat is given out during the reaction. It is exothermic. Enthalpies of combustion cannot be carried out in this way. The substance has to be burned in air. The flame heats up a calorimeter containing water. Let's look at an example involving combustion. A value for the enthalpy of combustion of ethanol was determined in the laboratory. The following results were obtained. When magnesium is added to dilute hydrochloric acid, magnesium chloride and hydrogen are formed. If hydrogen gas is bubbled through magnesium chloride solution, magnesium and hydrochloric acid are not formed. This is an irreversible reaction, as indicated by this sign. We know that most chemical changes are irreversible, but some chemical changes are reversible. This is a reversible reaction, as indicated by this sign. The chromate 6 ion is yellow. When acid is added, the hydrogen ions cause the equilibrium to shift to the right and the colour changes to orange, which is the colour of the dichromate 6 ion. Addition of alkali reverses this and the colour changes yellow again. How can this be explained? Some industrial processes involve gaseous equilibria. In industry, chemists must consider how to obtain a good yield of product at a reasonable cost of process and safely. The factors which affect gaseous equilibria are the pressure and the temperature at which the reaction is carried out. Gaseous reactions take place in sealed vessels, otherwise the gases would diffuse away and not react. Gas pressure is exerted on the walls of the container as the gas molecules collide with the walls. The more molecules there are present, the higher the collision rate and the greater the pressure exerted. Let's consider the Haber process, the manufacture of ammonia from its elements nitrogen and hydrogen. In this equilibrium, there are 4 moles of reactant molecules and 2 moles of product molecule. Increasing the pressure shifts the equilibrium to the right, so that the system lowers its own pressure by reducing the number of molecules present. It counteracts the change. This change produces more ammonia. High pressure is needed for a good yield of product, but attaining and maintaining very high pressure is expensive, and enclosed systems at very high pressures are dangerous and susceptible to explosion. The equilibrium from left to right is exothermic. An increase in temperature will shift the equilibrium to the left. The system will absorb the extra heat energy and shift in the endothermic direction. It counteracts the change. This change produces less ammonia, so a lower temperature is needed for a good yield of product, but a low temperature results in a slow rate of reaction and time costs money. A catalyst is also added to speed up the reaction. It enables the reaction to be fast enough at a low enough temperature to give a good yield of ammonia. A catalyst has no effect on equilibrium position. It speeds up both the forward and backward reactions to the same degree, but it does speed up the attainment of that equilibrium. Under the conditions given, the yield of ammonia in the gases leaving the reaction vessels is only in the order of 15%. 85% of the gases are unconverted. What is done in industry to counteract this? Well, the unreacted nitrogen and hydrogen gases are recycled, improving the yield. Remember, if a change is imposed in a system in equilibrium, the system will move to oppose the change.
Reaction kinetics is the study of the rate of chemical reactions and the factors that affect the rate. Remember that all matter is made up of particles and that in a chemical change, atoms rearrange to form new chemicals. For this to happen, the particles must collide, and this is known as the collision theory. But do all collisions between particles lead to chemical change? Only those particles with sufficient energy on collision will react to give products. This minimum energy is the activation energy for the reaction and is given the symbol EA. What happens if the total energy on collision is lower than the activation energy? The particles will stay as they are. Molecules in the gaseous and liquid states are in constant random motion, and as molecules collide with each other and with the container walls, their energies change. This means that the particles will have a variety of different energies throughout the physical state. There is a distribution of energies known as the Maxwell-Boltzmann distribution, which is represented by a Maxwell-Boltzmann distribution curve. Let's look at the curve in detail. Note that there are no molecules with zero energy. There is no maximum energy. Very few molecules have very high energy. The most probable energy a molecule has is E1. The average energy, E2, is to the right of the maximum energy, E1. The area under the curve represents the total number of molecules present in the sample. EA is the activation energy for the reaction. Only the molecules to the right of the activation energy have sufficient energy to react chemically on collision. Rates of reaction are very important in the chemical industry. Time costs money, and the rate at which a chemical is manufactured will affect the price of the final product. When we talk about the rate of a reaction, what do we mean? The rate of a reaction is measured as the rate of change of concentration of a reactant. The unit of concentration is moles per decimeter cubed, and if the unit of time is seconds, then the rate is measured in moles per decimeter cubed per second. What can affect the rate of a chemical reaction? The factors which change the rate of a reaction are the concentration of a reactant, the surface area of a reactant, pressure, temperature, and the presence of a catalyst. How do these factors affect the rate of a reaction? Increasing the concentration of a reactant increases the rate of reaction. Concentration applies to aqueous solutions, and it is a measure of the number of moles of solute particles in a given volume of solution. With a higher concentration, there are more reactant particles in the volume of solution, so the chance of collision between these particles is greatly increased. If the rate of collision increases, then the rate of reaction also increases. For gases, increasing the pressure has the same effect. The gas is compressed, forcing the particles closer together and increasing the chance of collision. The rate of reaction can be determined by measuring either the fall in concentration of a reactant or the increasing amount of a product. Let's look at a graph showing fall in concentration of a reactant as the reaction proceeds. The rate of reaction at any given time is given by the slope or gradient of the curve. The slope is negative because the concentration of the reactant is decreasing as it is used up. The rate of reaction is fastest at the start, where the negative gradient is steepest and the concentration of the reactant is at its maximum. As the reaction proceeds, the slope becomes less negative. The reaction rate has decreased as reactant particles are being converted into product particles, and their concentration is decreasing. The gradient is zero when the reaction is completed. The rate of a reaction is affected by the particle size of a solid reactant. Reaction takes place at the surface of the solid where the other reactant particles collide. For a given mass of solid, the smaller the particles, the greater the surface area available for collision. This increases the collision rate, and so the rate of reaction increases. So, smaller particle size gives a faster reaction. In the reaction between marble chips and dilute hydrochloric acid, the rate of reaction can be found by measuring the amount of carbon dioxide gas produced at regular time intervals. How can this be done? Either by weighing the apparatus and chemicals at regular time intervals to determine the loss in mass. The lost mass is the mass of carbon dioxide gas produced. Or by measuring the volume of carbon dioxide produced using a gas syringe. A graph of either of these quantities can be plotted against time. Here is a graph of volume of carbon dioxide formed against time. Note the gradient of the curve is positive because carbon dioxide is being produced, not used up. Also, the gradient of the curve is greatest at the beginning, where the reaction is at its fastest. But why should that be? Because the concentration of hydrochloric acid is at its highest at the start of the reaction. As the reaction proceeds, the slope of the curve becomes less steep. Why? Because the concentration of the acid is decreasing. What is happening here? The reaction has finished, either because all the acid has been used up or all the marble chips have reacted. When the reaction has finished, some of the reactant which is in excess will remain unreacted. If the reaction is repeated with the same mass of smaller marble chips, we get a curve like this. The initial gradient of this curve is steeper because the smaller particle size gives a bigger surface area for the acid particles to collide with. The collision rate is higher, and so the reaction rate is faster. So, why do both curves finish up at the same level? The same mass of marble chips was used in both experiments, so the same final volume of carbon dioxide was produced. As well as the mass being the same, the other factors that must be kept constant to ensure a fair comparison between the different sized chips are the temperature, the concentration of hydrochloric acid, and the volume of acid. An increase in temperature considerably increases the rate of a reaction. This is because there are two contributing factors. Firstly, the particles gain kinetic energy, move about more quickly and collide more often. And secondly, more collisions exceed the activation energy for the reaction. So a greater proportion of particle collisions give rise to product formation. This second factor has a big effect on the rate. And as a general rule, doubling the temperature results in a reaction that is 10 times faster. Let's look at the effect on the distribution curve. The final factor we need to look at is the use of a catalyst. A catalyst alters the rate of a chemical reaction, but is chemically unchanged at the end of the reaction. It increases the rate by providing an alternative route for the reaction to take, which has a lower activation energy. Let's look at a reaction profile to show this. Now, remember, the catalyst does not increase the energy of the reactant particles, nor does it increase the number of collisions with energy greater than the activation energy. But it does provide an alternative route for the reaction to take, a route which requires a lower activation energy. This enables particles with lower energy to collide and form products. By lowering the activation energy of a reaction, many more molecules are able to react compared with the reaction when no catalyst is present. So, the rate is increased.
Redox reactions and Group 7 chemistry. Redox reactions involve both oxidation and reduction. But what do we mean by these two terms? Well, oxidation can simply be described as the gain of oxygen, but it is also the loss of hydrogen, the loss of an electron, or an increase in oxidation number. Conversely, reduction is loss of oxygen, gain of hydrogen, gain of electrons, or a decrease in oxidation number. In this reaction, ammonia has been oxidized. Why? Because it has lost hydrogen and formed nitrogen. Which reactant is reduced? The copper oxide, as it has lost oxygen and formed copper. The next bit is often confused. The reducing agent in this reaction is ammonia. Why? Because the reducing agent causes the other reactant to be reduced, but it is oxidized. So what about an oxidizing agent? It causes the other reagent to be oxidized and is itself reduced. The oxidation states of elements are used to identify whether or not a reaction is redox. In this concept, all atoms are treated as ions, even if the bonding is covalent. Here are the rules. Uncombined elements have oxidation state 0. Metals in groups 1 to 3 have oxidation states equal to the charges on their ions. Non-metals, present as ides, have oxidation states equal to the charges on their ions. Hydrogen has oxidation state +1, except in hydrides of metals. Oxygen has oxidation state number -2, except for a couple of exceptions. Transition elements have a variety of oxidation states, and the oxidation state in a particular compound or ion may have to be determined by calculation. In order to determine the name of a compound or ion, or whether a reaction is redox or not, we need to remember that the total sum of all the oxidation states of elements in a compound is 0, and the sum of the oxidation states of elements in an ion must equal the charge on that ion. Let's look at some examples. In order to identify a redox reaction, we must look at the oxidation states of each element on both sides of the equation. If there are changes in oxidation state, the reaction is redox. If there are no changes, it isn't. What about calcium and water? Calcium changes oxidation state from 0 to +2. Hydrogen changes oxidation state from +1 to 0. So this is a redox reaction. Remember, when there is an increase in oxidation state, oxidation has taken place. When there is a decrease in oxidation state, reduction has taken place. Let's explain the previous reaction in terms of oxidation and reduction. It's best represented by an ionic equation. Now, if we add the oxidation states, we can see that the calcium has been oxidized to Ca2+. It has increased in oxidation state from 0 to +2. The H+ has been reduced to H2. It has decreased in oxidation state from +1 to 0. Let's look at another equation. And putting in the oxidation states, we can see that there are no changes. Magnesium remains at +2, oxygen remains at -2, hydrogen remains at +1, and sulfur remains at +6. So this is not a redox reaction. Redox reactions involve a transfer of electrons. Oxidation involves a loss of electrons. Reduction involves a gain. Remember, oil rig. Oxidation is loss, reduction is gain. In the reaction between zinc and copper-2 ions in aqueous solution, there are two half equations. Zinc is oxidized to Zn2+. It loses 2 electrons. And copper-2+ is reduced to copper. It gains 2 electrons. So, which reactant is the reducing agent? Zinc, because it is oxidized and loses 2 electrons. Cu2+ gains these 2 electrons and is reduced to copper. You ought to be able to construct oxidation and reduction half equations from a full redox equation. How? Well, using oxidation states, identify the species which are oxidized and reduced. Write and balance half equations for each in turn, remembering to balance both the numbers of atoms and the charges. Let's use the reaction between iron 3 ions and iodide ions as an example. Okay, adding the oxidation states, we can see iron 3 is reduced to iron 2, and iodide is oxidized to iodine. Write the half equation for iron. You can see that the iron atoms are balanced, and 1 electron is added to the left-hand side to balance the charges. Okay, now the iodide half equation. A 2 is needed in front of I- to balance with I2, and 2 electrons are added to the right-hand side to balance the charges. Now let's look at the process of writing the full equation from half equations. Manganese 4 oxide, MnO2, reacts with concentrated hydrochloric acid to produce chlorine gas, manganese 2 ions, Mn2+, and water. From this information, we can construct each half equation, then deduce the full redox equation. Mn2+ ions and water are formed from MnO2 and the H+ ions from the acid. First, balance the number of atoms. Now, balance the charges. On the left-hand side, we have 4+ and 2+ on the right-hand side. So 2 electrons need to be added to the left-hand side. The chloride ions from hydrochloric acid have been converted into chlorine. Balance the chlorine atoms, then balance the charges. These are 2- on the left-hand side with no charge on the right-hand side. So add 2 electrons to the right-hand side. Now, bring the 2 half reactions together. We can see the electrons lost and gained are balanced. So we can now add the 2 half equations together. Remember that a full redox equation must not contain electrons. They need to be balanced, and if they are, the electrons on each side of the equation cancel out. The elements of group 7 are called halogens. Being on the right of the periodic table, they are nonmetals, and being members of a group, they have similar chemical properties. There is a clear trend in both physical and chemical properties as the group is descended. Okay, let's look at these trends. They exist as diatomic molecules with formula X2. Both the atomic and ionic radii increase as the group is descended, because as the group is descended, an extra shell of electrons is present. Their boiling points increase as the group is descended, because the molecules increase in size. There are more electrons, and the van der Waals forces between the molecules increase, so more energy is needed to force them apart. Their electronegativities decrease as the group is descended. Why? As electronegativity is the power of an atom to attract the bonding pair of electrons in a covalent bond, and the atoms increase in size as group 7 is descended. There is a decrease in electronegativity because the positive nucleus is further from the bonding pair, and there are more filled inner electron shells shielding the nucleus and effectively reducing the attraction. The halogens are oxidizing agents. A group 7 element needs to gain 1 electron to become stable, and the molecule, X2, therefore needs to gain 2. X2 gains electrons and is reduced to X-. It is, therefore, an oxidizing agent. This equation involves the XX bond breaking, the ion X- forming, and then forming an aqueous solution. Taking these factors into consideration, oxidizing power decreases down the group. So chlorine displaces both bromine and iodine from aqueous solution. Bromine displaces iodine but not chlorine, and iodine displaces neither chlorine nor bromine. These are redox reactions. With chloride, there is no further reaction. No redox reaction occurs. The chloride ion does not act as a reducing agent. It does not reduce sulfuric acid. With sodium bromide, the hydrogen bromide gas formed reduces the sulfuric acid to colourless sulfur dioxide gas. It is itself oxidized to brown fumes of bromine vapour, Br2. With sodium iodide, the hydrogen iodide gas formed reduces the sulfuric acid to sulfur dioxide, yellow solid sulfur, and hydrogen sulfide, which smells of bad eggs. A redox reaction in which one element is both oxidized and reduced at the same time is called a disproportionation reaction. For example, if sodium hydroxide is used, sodium chloride and sodium chlorate 1 are formed. Here is an ionic equation to illustrate this. When testing for chlorine gas in the laboratory, moist blue litmus paper first turns red as the 2 acids are formed, and then the chloric 1 acid bleaches the paper and removes the colour. Chlorine reacts with alkalis to give 2 salts. Notice that the chlorine disproportionates. The chlorate 1 ion, ClO-, causes bleaching, and the mixture of sodium chloride and sodium chlorate 1 is sold as household bleach. Silver halides are very insoluble, and halide ions in aqueous solution can be identified by a precipitation reaction. The test involves using an aqueous solution of the halide, then adding dilute nitric acid, followed by silver nitrate solution. Why add dilute nitric acid before adding silver nitrate solution? To remove any carbonate ions that may be present. Silver carbonate is insoluble and is formed as a white precipitate if carbonate ions are present. The colour of the precipitate helps identify the halide ion. To further enhance the test, the solubilities of the silver halides in ammonia solution are used. This is what you would expect to happen. How would you test to show the presence of the iodide ion in aqueous solution? First, add dilute nitric acid, followed by silver nitrate solution. You should get a yellow precipitate of silver iodide. Next, add concentrated ammonia, and the precipitate stays as it is insoluble in concentrated ammonia.
The extraction of metals. Metals are important in today's world. They are strong, malleable, ductile, and good conductors of both heat and electricity. They have numerous applications, particularly in the construction industry. But where are they to be found? Very few metals exist as separate elements on Earth. They are in minerals that are present in rocks found in the Earth's crust. They have to be extracted from their naturally occurring ores. Metal ores usually contain the metal as its oxide or sulfide. Metals are extracted from their oxide, so first, the sulfide ores must be converted to oxides. The sulfides are roasted in the air to form the oxide. Unfortunately, the sulfur dioxide gas formed during the roasting of sulfide ores causes the formation of acid rain. Acid rain damages plants and pollutes lakes. Extracting a metal from its oxide is reduction. A reducing agent which occurs naturally is less expensive than one which has to be made by another process. In the extraction of iron in the blast furnace, the reducing agent used is coke, which has a very high carbon content. It is obtained from coal, which is naturally occurring by heating the coal in the absence of air. The raw materials needed for the process are hematite, which is naturally occurring iron 3 oxide, coke, limestone, and air. Hematite, coke, and limestone are fed in at the top of the furnace. Hot air is blown in near the bottom. The coke reacts with oxygen from the hot air. This reaction is very exothermic, and the temperature rises to around 1500 degrees C. The next reaction is endothermic and needs this high temperature in order to take place. The carbon dioxide reacts with coke higher up the furnace to form carbon monoxide, causing the temperature to fall. Further up the furnace, the carbon monoxide reduces the iron 3 oxide to iron. At around 1200 degrees C, the temperature here is also hot enough for some iron to be formed by the reduction of iron 3 oxide with coke. Both carbon and carbon monoxide are reducing agents or reductants. Note that at these temperatures, iron is in the liquid state. It runs to the base of the furnace where it is tapped off. But why is limestone present in the furnace? The main impurity in hematite is silicon 4 oxide or sand. Limestone, or calcium carbonate, undergoes thermal decomposition to give calcium oxide and carbon dioxide. Calcium oxide is a base. Silicon 4 oxide is acidic. As we know, a base and an acid will react to form a salt, in this case, calcium silicate. The product of this reaction is called slag. It is molten and runs to the base of the furnace. Calcium silicate is used in the construction industry to make breeze blocks. So, limestone is added to the furnace to remove the acidic oxide impurities in hematite. The process is continuous. More raw materials can be introduced at the top of the furnace as iron is tapped off at the bottom. The iron produced in the blast furnace is impure. It contains sulfur, carbon, silicon, phosphorus, and manganese. Most of the iron produced is used to make steel. Steel is an alloy of iron and carbon and is produced from iron by the basic oxygen steel making process, BOS. This process involves the removal of impurities from the pig iron produced from the blast furnace. Sulfur is removed prior to the BOS process. The impure iron is desulfurized by heating with magnesium or calcium. The sulfides are molten and float to the surface of the iron. This slag can be scraped off the surface. The iron is now transferred to the basic oxygen converter and scrap steel is added. Lime, calcium oxide, or limestone, calcium carbonate are also added. The converter is heated and the iron melted. Preheated oxygen is then blown onto the molten iron. How is each impurity removed by this process? Well, carbon is oxidized to carbon monoxide gas, and silicon, phosphorus, and manganese all form their oxides. These oxides react with the basic calcium oxide to give a molten slag, which floats above the iron and can then be scraped off. Why can calcium carbonate be used in place of calcium oxide? At the temperature present in the converter, it will undergo thermal decomposition and form calcium oxide. So why is sulfur removed before the BOS process? Surely it would burn in the oxygen in the converter to give sulfur dioxide gas and be removed. But in fact, iron would be oxidized in preference to sulfur. Not all of the carbon present in the iron is removed, and the carbon content of the steel produced is between 0.04% and 1%. Why isn't all the carbon removed? Because pure iron is too soft. So what is the problem with higher carbon content, I hear you say? The steel is too brittle. Thermodynamics shows that all oxides of metals can be reduced to the metal by heating with carbon, but oxides of the more reactive metals, such as aluminium, need far too high a temperature for the process to be economically viable. Some react with the carbon to give metal carbides rather than the metal. For example, when rutile, titanium 4 oxide, is heated with coke, titanium carbide is formed rather than titanium metal. Other oxides that give carbides are molybdenum, tungsten, and vanadium. Aluminium oxide is very stable. Aluminium is extracted by electrolysis. The naturally occurring ore of aluminium used in the process is bauxite, aluminium oxide. It is first purified to give alumina. In order for electrolysis to be carried out, the aluminium oxide must be molten. Why? Liquid ionic compounds contain freely moving ions which must be present if electricity is to be conducted. In a solid, ions only vibrate about a fixed point, but its melting point is very high. It is above 2000 degrees C. How is this lowered and the process made more economical? By dissolving it in cryolite, another naturally occurring ore of aluminium. The melting point is reduced to approximately 970 degrees C, saving considerable costs in heat energy. During electrolysis, aluminium ions move to the cathode and are discharged, producing molten aluminium. This is reduction by electrolysis. Oxide ions move to the anode and are discharged as oxygen gas. The anode is made of graphite. At the high temperature of the process, this carbon anode reacts with the oxygen to form the gaseous oxides of carbon, carbon monoxide and carbon dioxide. The anodes burn away. The process is continuous. Regular additions of aluminium oxide are made to the cell, but the graphite anodes need replacing on a regular basis, and the cost of electricity is high. Electricity is required to provide the high temperature of 970 degrees C and decompose the aluminium oxide by electrolysis. 3 moles of electrons are needed to produce each mole of aluminium, just 27 grams. The disposal of waste cryolite is a problem because it causes fluoride pollution. However, despite the negatives, aluminium has many useful applications and is manufactured on a large scale. Another very useful metal is titanium. Titanium is found in abundance in the Earth's crust and is used extensively in engineering. It has low density, is very strong, and has a high resistance to corrosion. But it must be in a very pure form. Rutile is a naturally occurring ore of titanium. It is titanium 4 oxide, and the extraction of titanium from this has 2 stages. The ore is heated with coke to a temperature of 900 degrees C in the presence of chlorine gas. The resulting titanium 4 chloride formed is a liquid and is purified by fractional distillation under an argon or nitrogen atmosphere. Why is this atmosphere needed? Because moisture in the air would hydrolyze titanium 4 chloride and give misty fumes of hydrogen chloride gas. The purified titanium 4 chloride is reacted with sodium or magnesium at 550 degrees C. This redox reaction is exothermic and temperatures reach as high as 1000 degrees Celsius. How do you know this is a redox reaction? In the reaction with sodium, the titanium changes oxidation state from +4 in titanium 4 chloride to 0 in titanium. It has been reduced. The oxidation state of sodium changes from 0 in sodium to +1 in sodium chloride. It has been oxidized. The titanium has been displaced by a more active metal. An inert atmosphere of argon is needed to prevent the titanium metal reacting with either oxygen or nitrogen in air. Finally, titanium is separated from the sodium chloride by the addition of water. Sodium chloride dissolves and can be washed out, leaving granules of titanium. There are high costs involved in this process, and so titanium is an expensive metal. How is it possible to get the titanium so pure? Okay, now in the first stage of the process, titanium 4 chloride liquid is formed. Liquids can be purified by fractional distillation. The pure titanium 4 chloride eventually yields pure titanium. Why is titanium required in such a pure state? Because in its engineering application, it needs to be hard and strong. Traces of elements such as oxygen, nitrogen, or carbon render the metal brittle. There is a high natural abundance of titanium on Earth, and it has unique properties. Why has it such limited use? Mainly because it's very expensive to extract. Both iron and aluminium can be recycled. Why is this a good idea? Scrap iron and steel are recycled using the electric arc process, in which an electric arc melts the scrap metal and the addition of lime removes impurities, converting them into slag. Recycling has many benefits, but on the downside, considerable costs are involved in collecting and separating scrap metal, aluminium in particular.